Hello everyone, welcome to the tutorial for chapter 12. It's the 13th chapter in the version 2 textbook. Whatever version you are using, in this chapter we will learn about the same thing, the multi-level model. So what are multi-level models? Simply speaking, these models are like assigning priors on priors instead of assigning fixed priors. Or you can think of this multi-level model another way. Imagine that our model is consisted of a lot of layers. If our model has multiple levels of priors, means the model has multiple layers. When we are having multi-level model or multi-layer models, the parameters in the second layer of the model is controlled by the parameter in the first level, and the parameters for the third layer is controlled by the parameters of second layer. All the models we had been dealing with two-level models. The first level is the prior distribution, and the second level likelihood function. So we set the prior values manually in the first layer prior distribution, and then in the likelihood function, the parameters will be controlled by the prior distribution we set. What we will do in this chapter is that we will add another level of prior distribution above the prior distribution we have previously. So we will set the values individually for the top level prior, and the parameters of the second level prior and the parameters of the likelihood functions will be estimated under the top to down order. I know it's confusing, so let's get into one example. Considering a data with many clusters, tadpoles in different ponds, our goal is to estimate the survival rates of tadpoles in different ponds. I believe you are already familiar with this kind of question. What we usually do is that we will set a fixed prior for the survival rate at different ponds, like what I do in model 12.1.1. The data and variables we have are all in a very common setting. So we have tank, which means different ponds from tank 1 to tank 48, and we have the density in each tank and the survival count of each tank, and we just divide survive count divided density count. We will get the survival proportion, which is our y, and the predictors are size, like it's a big tank or a small tank or a middle tank. I didn't include any predictors and just use a binomial model to fit this regression problem. N means the initial count of tadpoles in each tank, and S means the survived count of tadpoles in different tank. Just simple logistic conversion. I estimate the P, which is kind of the mean of the survival rate of each tank. But notice that I'm not estimating the global mean of all the tank. I'm estimating the individual mean of each tank. So you can see it's from from 1 to number of tank here. This is the simplest setting, just like we are only estimating the intercepts of a linear regression model. In this setting, each of the parameters from the mean in tank 1 to the mean in tank 48, they are estimated independently with no information sharing between ponds because they are all randomly drawn from the prior normal 0, 1.5. They were drawn independently. However, this is not consistent with the reality. In the real world, we may gain more experience as we see more ponds, so our prior can be set adaptively, and the information between different ponds or different tanks can be shared with each other. Multi-level model can help us achieve the goal of information sharing between clusters through the usage of adaptive prior. Dive into the newer model. So you can see the data block isn't changed, and the parameters block, we had two more parameters. First is the A bar, the second is A sigma. You will know how these two parameters work in the later transform parameters block. Nothing has changed. The main difference are in the model block. You can see that now the parameters in the prior distribution are drawn from another prior distribution. So A is now drawn from normal A bar and A sigma. And A bar is from a normal 0, 1.5, and A sigma is from exponential 1. What it means is that A bar and S sigma will actually change according our data. There are few variations in the data, like the survival proportion of different tanks are very similar, then the A sigma value will be small. And if the average survival rate across all the tanks, all different tanks are higher, we will have higher A bar value. We have small mean values across all the tanks, we can have small A bar value. And the A here we want to estimate is the individual parameters for each tank. To sum up, the hyperprior level will be influenced by all the data, And the adaptive prior, or you can say the second level prior for individual tank, will be altered by all the information here, but not directly. So this is the key concept using multi-level model. And because the prior distribution for A will be changed according to what the data looks like, it's also called adaptive prior. After plotting the result, you can see that the estimated A bar is 1.34 and the estimated A sigma value is 1.61. So the adaptive prior for A is the normal 1.34 and 1.61. In comparison, the fixed prior we set, A follows normal 0, 1.5. So this fixed prior underestimating the A bar value and the A sigma value. Posterior result from fixed effect model and adaptive effect model and the raw data. On the horizontal axis, we record the tank index from tank 1 to tank 48. On the vertical axis, it's the proportion, the survival rate. The white circles are from the observed data. The pink circles, the pink points are from a fixed prior model, and the blue points are from a multi-level model. And the gray dashed line is the mean across all the tanks. Observe three interesting results from this plot. Firstly, the multi-level estimate, the blue points are closer to the dashed line than the row in the observed data. This phenomenon is called shrinkage effect. Since we borrow the information across all the different tanks, the variance in our multi-level model prediction will be smaller than the observed data. Also, the shrinkage effect is stronger in smaller tanks than medium tank or large tank. And the third observation is that a shrinkage effect is stronger when a tank's observed proportion is farther from the dash. So the shrinkage effect is stronger in these points, or these points, or these points. As you can see, the distance between the blue points and the white points is larger than these points, which are closer to the dashed line. Besides, you can notice that all the pink points are lower than the blue points. That's basically because the prior for A in the fixed effect model follows normal 0, 1.5, but in the adaptive effect model, the prior of A is 1.3 and 1.6 for sigma. Same strategy can be applied to data with more than one cluster as well. More than one cluster in the model, we want information to be shared only in the cluster, not across cluster, because that doesn't make sense. What we use to illustrate this idea is our offering, the chimpanzee data. We have 7 chimpanzees in total, and we want to test 2 factors, both with 2 kinds of treatments. So we have totally 4 treatments. So information could be shared for different chimpanzees, and the information can also be shared for different chimpanzees under same conditions. Let's see how to build this kind of model. The fixed prior model looks just like this, so we want to estimate using the binomial regression model for the rate of a chimpanzee pulling left, and we use the logic transformation to estimate the coefficient for actor effect, treatment effect, and block effect, and manually set the prior for these 3 coefficients. And then let's build an adaptive model. So we just need to replace the fixed priors of actor, block, and treatment effect with adaptive priors. Then the model will become a multi-level model. You might wonder that treatment was kind of fixed by the experiment. Why we need to set a fixed prior? Why we need to set an adaptive prior on them? However, the reason to use adaptive prior is because they provide better inference. Like I've mentioned, setting the adaptive prior allows the information to be shared across different groups of different data in the same group. So once the data is under the same cluster, then adaptive prior can help. Let's dive into the mathematical form of the adaptive model. So the only thing changed is the prior here. Now you can see that there are no fixed values in the prior distributions. I just set some insert some hyperparameters which will be estimated, and you can notice that alpha will be drawn from one prior distribution, beta will be drawn from one prior distribution, and gamma will have one prior distribution. So information will only be shared through these sigma values. So respectively to each of these 3 parameters, informations would not shared across different parameters. That there is only one mean parameter, the alpha bar, because we cannot identify a separate mean for each varying intercept type. because all intercepts are added together in the linear function. It's exactly the same logic for the right leg and left leg example. In Stan code, we just do the modification accordingly. So you can see we have 4 new parameters to be estimated, alpha bar, sigma alpha, sigma beta, and sigma gamma. And in the model block, now we have adaptive priors for alpha, beta, gamma, and hyper priors for alpha bar, sigma beta, and sigma gamma. It's not very difficult to move from the model with one cluster to a model with many clusters, like the chimpanzee's example. Let's compare these two models. So as you can see here, the model with adaptive prior, model 12.2.2, is slightly better with lower WAIC value. Besides, the second model has more details for us, so we can compare the 3 sigma values. On the x-axis is the value of the standard deviation, and on the y-axis is the cumulative count from Stan output. You can see that the variance in block, which is the sigma gamma parameter, is very close to 0, meaning that there is almost no variance between each block. We can further conclude that whether we include block variable or not doesn't matter in this case. On the other hand, you can also tell that the individual differences between different chimpanzees accounts for most of the variance in the data. Having this kind of information is another advantage of using a multi-level model. So, by default, we should use multi-level model to solve any problem. However, there is a serious problem must be solved to use multi-level model in Stan. If we look closer to the Stan output, we will notice that actually some of the R-hat values for the A's parameters, which means the model didn't converge. During the model fitting process, Stan also warned us there were some divergent transitions after warm-up. This means the simulation has some error compared to the ideal situation. If our model has many divergent transitions, then it might result in a biased posterior. This phenomenon is very common when fitting multi-level model in Stan, because when Stan is doing sampling, some parameters are relied or correlated with some other parameters. MCMC would not be able to run smoothly under this kind of situation. I will introduce 2 ways to deal with this problem. Simply increase the target acceptance rate as the Stan warn suggests. When target acceptance rate is set high, MCMC will sample with a smaller step size, which means a more accurate approximation on the curved surface. Well, it does help. Divergent transitions drop from 12 to 4 by setting the acceptance rate to 0.99. There are 2 problems. Firstly, setting a very high acceptance rate will lead to a long running time for a Stan model. So here the total running times 71 seconds, previous model, and the first model only take about 5 seconds to do all the sampling. What's worse, the problem is actually not solved perfectly. As you can see, some of the parameters are still having R-hat value larger than 1, like alpha 5 or beta 2, 3, 4, even gamma 1. So adjusting target acceptance rate is not the recommended solution to this problem. Second solution is a more hardcore solution called reparameterization. For any statistical model, it can be written in several forms that are mathematically identical. Some of them are easier to be sampled than others for Stan. Alpha follows normal mu sigma, and the second one, alpha follows mu plus sigma times a standard normal distribution, are mathematically the same statement. When mu and sigma are hyperparameters, like we did in a multi-level model. The second formula is easier for Stan to draw samples, because we kind of extract a mu out of the normal distribution here, so we can sample. So Stan can sample mu and sigma respectively. In the Bayesian statistics, the second form, standard normal distribution, mean equal to 0, standard deviation equal to 1, in the distribution statement is known as the non-centered parameterization. Let's learn to build a non-centered version of the multi-level model for the chimpanzee problem. Start is the centered version of multi-level model we've been using from the beginning of this chapter. So we have hyperparameters in the distribution statement. So how can we make this to a non-centered version? For the first thing we do is to extract the alpha bar out from the normal distribution of prior of alpha, the sigma alpha, sigma gamma, sigma beta out of the prior distribution in the centered version, and make it and multiply it with a standard normal distribution like we did here. Be careful that we don't need to modify the hyperprior distribution for alpha bar or sigma alpha, sigma gamma, or sigma beta. For these three sigma hyperparameters, they still follow the same exponential 1 prior distribution, and for alpha bar, we still follow the same normal 0, 1.5 prior distribution. We change the linear function and the adaptive prior here. Let's take a look at the STEM model and check what has been changed. The data block, the same. The parameters block, be careful, it's still the same. The parameters we want to estimate or we need to estimate for a centered version or a non-centered version model are the same. We make our first modification in the transform parameters block. As you can see now, the linear model have been changed here. Now it's alpha bar plus alpha times sigma alpha, beta times sigma beta, and gamma times sigma gamma. And in the model block, our second modification, the adaptive priors have also changed. They are now just the standard normal distribution. Let's look at the fading time and see if we still have any divergent transitions. So firstly, the fading time, okay, 11 seconds, although it's a little bit longer than the centered version, but it's not a huge difference. And then for divergent transitions, you can see with the non-centered model now, divergent transitions is 0. Also compare the number of effective samples of these three models on different parameters. So larger effective samples means parameters is sampled better. Model C, the non-centered version, usually has the most effective samples. Two methods, adjusting the target acceptance rate or reparameterization in the model, also the problem of divergent transitions. But from the above result, we can tell that the non-centered version model has significantly more effective samples. Besides, reparameterization has the advantage of shorter runtime when the dataset is large. But we also need to keep in mind that in some situations, actually the centered version of model is better for STEM to do the sampling. Even in some extreme situations, the centered form could be better for one cluster in a model. Non-centered version will be better for another cluster in the same model. For example, it's possible that in the chimpanzee data we just used, the best way to solve that problem may be using a centered version for the treatment effect and using a non-centered version for block effect and chimpanzee effect. The key takeaway is that you have to be familiar with a different kind of parameterization. So when one of them doesn't work, you can switch to another form, kind of pray for a better result. This example is the simplest way to do reparameterization. In next chapter, we will have some more complicated examples, so you will gain more skills doing parameterizations. In the last part of this tutorial video, we will learn about making predictions in multi-level model. The situation will be a little bit different when we are making in-sample prediction or out-sample prediction. In-sample prediction is like when we want to make the prediction for an existing tank of the tadpole example or an existing chimpanzee, one of the 7 chimpanzees in our data. But if we instead wish to compute predictions for some new data set, like a new tank of tadpole or a new chimpanzees, the techniques are a little bit different. Chimpanzee example to illustrate the differences between in-sample prediction and out-sample prediction. To use 2 ways to do this. Either in-sample prediction or out-sample prediction by using standard genetic quantities block or using the apply method. I believe most of you are familiar with STAN and R now, so I won't talk about too many details, but just the ideas behind these 2 methods. In-sample predictions are like doing backtesting. Here, I will use the non-centered version model to make the backtest prediction for the second chimpanzee in block 1. To predict the chimpanzee's reaction under different treatments from treatment 1 to treatment 4. Talk about the STEM method first. The first step is to make a data frame containing the predictors we want to make backtest from. You can see we want to backtest on the second chimpanzees on block 1 and with a different treatment 1, 2, 3, 4. And then we need to make some small modifications on our STEM model. In the data block, we need a new place to insert our testing data. So you can see here, it's the number of predictions we're making for predictions, the different predictors value, so actor values, treatment values, and block values. And then for the main structure of the model, which means the parameters block, transform parameters, or the model block, we don't need to change anything. In the generated quantities block, we can add a new for loop, just like we did in your first assignment. We just need a new block to iterate through each row of the testing data. The linear model here is exactly the same as in transform parameters. The only difference is that in transform parameters, the data we input is the training data, and in generated quantities block, the data we have here is the testing data. So outside stand, we just need to modify the data list, the input data list here, and then we just extract the results like we did in our linear model. So we can have the same confidence interval and mean prediction as usual. So this is our backtest predictions for chimpanzee 2 in block 1 under treatment 1, treatment 2, treatment 3, and treatment 4. The gray area are the confidence interval and the black line is the prediction mean. The advantage of this apply method is that we don't need to recompile a new STEM model when we are doing in-sample prediction or out-sample prediction or any other thing. Instead, we can just use the posterior output directly. First step is to use another way to extract the samples from the STEM output. Before, we just use the as.data.frame function, but here we need to use the extract function from rstan. Output of the rstan extract is a named list. You can see now different parameters are stored in a separated data frame. Unlike the output of the as.data.frame function, where the output is just one table containing all different parameters. The output of one parameter's value, like the alpha value matrix like this. So if we want only the alpha value for the 4th chimpanzees, we just need to type a function like this. We will have the whole 2000 samples from STEM. This allows us to set up a customized link function easily. To avoid using for loop, which is very slow in R, we can optimize our code by using apply and a customized function. Function we make is like this. Given actor and block ID, we can change different treatment values from 1 to 4. Each treatment with its 2000 samples will be multiplied with the 2000 samples of block effect, of gamma effect and alpha bar. The with function here will make your code a simplifier. By using the with function, you don't need to select the alpha bar parameters like we did using post $ alpha bar. You just need to type alpha bar directly. And then we can apply function to loop over a treatment 1 to treatment 4 and get a result like this. The result is a 2000 by 4 matrix, which are the same predictions from STEM generated quantities output. We can use the same code to make the same plot. If we put the two plots together, you cannot tell any difference. It just depends on which method you prefer. The results are exactly the same. In the last part of this tutorial, we will learn about outsample prediction. We would like to make predictions about the whole species, not just the 7 chimpanzees we have, or we somehow get a new 8th chimpanzee, and before do any treatments on it, we want to have some prediction. It's time for outsample prediction. In this kind of setting, the individual actor intercepts aren't of interest, but the distribution of them is. In this kind of situation, we need to find a way to define the chimpanzee effect and block effect for alpha and gamma. Thus, we will be able to test different treatment effects. Since there are few variations in block effect, we can simply drop it. Unlike in sample prediction, we can assign like chimpanzee 1 or chimpanzee 2, 3, 4, 5, or chimpanzee 7 as our alpha. For outsample predictions, we need a way to define kind of an average chimpanzee. There are two ways to define an average chimpanzee. We borrow the ideas from confidence interval and prediction interval. The confidence interval way of defining average chimpanzee is to just use the alpha bar value. The prediction interval way is to draw some samples from the distribution, from the normal distribution of alpha bar and sigma alpha. The CI way of making predictions has less variation. Variation in the results are all from the treatment effect. However, the PI way of making predictions accounts for the individual differences between different chimpanzees. So it's always a good idea to include both way of results in your outsample prediction. I will call the CI prediction P bar and the PI prediction P simulation, just for convenience. Both P bar and P sim can be estimated in either STEM generated quantities block or the apply method. Let's begin from using STEM. It will be easier to think of the chimpanzee effect or alpha effect from the centered version of model. Originally, the chimpanzee effect alpha actor is just drawn from a normal distribution of alpha bar and sigma alpha. In the non-centered version model, actually we just factor out alpha bar and sigma alpha. But the two models here are still mathematically identical. So the alpha bar here is the alpha bar here. The sigma alpha here is the sigma alpha here. In the generated quantities block, if we want to make a p-bar prediction, we only need to use alpha bar to represent an average chimpanzee. And for the p-sim prediction, we randomly draw a sample from the normal alpha bar sigma alpha distribution for each prediction. With these two extra lines, Stan will calculate the p-bar and p-sim and store the results in the output file. So again, we can use the s.data.frame function and extract a p-bar and p-sim, and then put them to the same code we've been using from the beginning of this semester, and you will get the two results. The p-bar it has narrower interval, while p-sim has wider intervals, because p-sim take the variation of sigma alpha into consideration as well. Lastly, we can try to use the apply method. So using apply, we don't need to change anything in the STEM model. We just need to use the same posterior samples we extracted before. So the post here is the same post data in sample prediction. Basically, we follow the same logic as we did in STAN. So here is the function we put in the STAN generated quantities block. So we only need alpha bar and plus beta treatment times sigma beta to calculate p bar. For p-sim, it's a little bit different because we need to have some random samples from the normal alpha bar sigma alpha distribution. To make the code easier to read, I draw the normal samples outside the link function. In this line of code, I draw 2000 samples from 2000 pairs of alpha bar and sigma alpha, which means 2000 normal distributions. And I put asim in the link function for psim prediction and replace the alpha bar in the p bar link function. And we can put our customized link function into apply or supply. This is the last graph of this tutorial. I compare two ways of making two kinds of predictions to convince you that all these methods are the same. I know it's one of the longest tutorial video. I'm very glad if you finish the whole of it. So don't give up here because we are only one chapter away from the end of this semester. Let's kill it together!